Now, when you hear the word bi, what do you think of? Bi is associated with the number 2. And so binary numbers have only 2 possibilities, 0 or 1. Now, when dealing with circuits, 0 is, or it corresponds to a circuit being in the off state. 1 corresponds to a circuit being in the on state. So if you're dealing with true and false statements, an off state will be considered false, and on state would be considered true. If you're dealing with voltage, an off state would have 0 volts, and an on state, typically 5 volts, but something other than 0. Now, before we go over and, or, and not gates, let's talk about the buffer gate. So here is the symbol of the buffer gate. And it basically looks like a triangle. Pointing towards the right. On the left, we have the input. On the right, we have the output. So we're going to call the input A. The output will also be the same. So if we were to make a truth table, with the input and the output, if the input is on, which means it has a binary number of 1, the output will also be in the on state. If the input is in the off state, which means it has a binary of 0, the output will have the same binary number of 0 as well. Now let's draw a circuit to represent this. And the principal element of this circuit will be an NPN transistor. This is the base, this is the collector, and this is the emitter. Now we're going to connect this to a power source, and we're also going to use a light emitting diode. Now the light emitting diode, it's going to represent the output of the circuit. And let's connect this to a voltage source. So here is the input, which we'll call it input A. And what's going to happen if we apply a voltage to point A? So if the input is in an on state, will the LED, will it be on or off? Well, once you apply a voltage to the base, the transistor will turn on. Current will flow from the collector to the emitter. Therefore, the LED will be in an on state. So this corresponds to a 1 for the input and the output. Now, what about if the input is off? So in this case, we have a 0 at the input. If there's no voltage at the base, then the transistor will be off. No current will be able to flow from the collector to the emitter. So therefore, the LED will be off as well. And so that's basically the buffer logic gate. So if you have a 1 in the input, you're going to have a 1 in the output. If you have a 0 in the input, you have a 0 in the output. Now the next type of logic gate that we're going to talk about is the NOT gate. So here is the electrical symbol for it. It looks like a buffer gate, but it has like a circle in the front. Now let's call the input A. The output will be the complementary of A. You can also write it as A bar. Now let's write a truth table. So we're going to have the input and the output. So if we have a 0 at the input, the output will be a 1. And if we have a 1 at the input, the output will be 0. It's always going to be the opposite. So basically, if the input is in an off state, the output will be in an on state, and vice versa. Now, how can we represent this using a transistor circuit? The circuit is going to be very similar to what we drew before, but there's going to be one key difference, and that is the location of the LED. So here is our voltage source, and on the left we have our input A. The emitter is attached to the ground, but the LED will be connected across the collector of the transistor and the emitter. So once again, this will be our output. So let's say if the circuit, or rather input A, is in the on state. Will the LED be in the on state or the off state? Well, let's analyze it. So once we apply a voltage to the base of the transistor, current will be able to flow from the collector to the emitter. So current will flow from the positive 5 volts through the resistor. Now, once it gets to this point, it has two options. The current can flow to the right, or it can flow to the left. Now, electricity will always take the path of least resistance. And if the transistor is on, then the path of least resistance is from the collector to the emitter. So therefore, therefore, no current will flow in this direction. So this will be in the off state because the current has been diverted through the transistor. So notice that we have a complementary situation. The input is on, but the output is off. Likewise, the reverse is true. So let's say that the input is off. There's no voltage applied at input A. So what's going to happen? Current will still flow through the resistor. Now, once it reaches this point, because the transistor is off, it cannot flow through the transistor. So therefore, it has no choice but to flow through the LED. So therefore, the LED is in an on state. So as we can see here, if we have a 0 at A, the output will be a 1. And if we have a 1 at A, the output is a 0. And so that's the basic function of a NOT gate. It turns an off state into an on state and vice versa. It turns A into A prime. Now the next logic gate that we're going to talk about is the AND gate. And here is the symbol for an AND gate. We're going to have two inputs, A and B, and the output will be A times B. Now let's write a truth table. And at the same time, let's draw a circuit for this. So we're going to need two transistors as opposed to one. So this is input A and this is input B. And let's connect it to a voltage source. So what happens if input A and B are in an off state? Will the LED be on or off? In this case, both transistors will be off. So no current can flow from the positive 5 voltage source to the ground. So therefore, the output will be a 0 to the ground. So therefore, the output will be a 0 because the LED is off. Now, what if A is in an on state and B is in an off state? Will the LED be on or off? Current can flow through the resistor, through the LED, and through the first transistor. However, because the second transistor is off, no current can flow through it. So therefore, no current will flow through the LED. So the LED will be in an off state. So we're going to put a 0. The only way the LED can be on is if both inputs A and B are on. Only under that circumstance can current flow through the LED and through both transistors to make it to the ground. So thus we have the word and. The only way the output can be in an on state is if both inputs A and B are on the on state. So even if B is on and A is off, no current will flow through the LED, only if A and B are on. Now let's move on to the OR circuit. And let's begin by drawing the symbol for that. So here's how it looks like. So let's say this is input A and B. Now it's not going to be A times B as in the case of an AND circuit, but it's A plus B for the OR logic gate. Now let's make a table just like before. And let's draw a circuit that corresponds to it. So this time what we're going to have is 2 NPN transistors. But they're going to be connected parallel to each other to make the OR logic gate. In the case of an AND logic gate, they were connected in series with each other. And so that's the key difference between the AND and OR logic gate. Now let's say that transistor A and B are in the off state. Will the LED be on or off? So clearly, no current can flow through the first transistor or through the second transistor. So therefore, no current will flow through the LED. The LED will be off. So we can put a 0 in the truth table. Now what about if the first transistor is on, but the second one is off? What's going to happen? Current can flow through the resistor, through the LED, but through the transistor that is on. So therefore, there's a path from the positive voltage source to the ground. Is on, but this time is so here is basically the complement of the AND gate. So here is the symbol for the AND gate. The NAND gate symbol looks very similar. The only difference is we're going to have a circle at the end. So let's say this is input A and this is input B. The output of an AND gate, we said it's A times B. For an AND gate, it's going to be the complement of A times B. Now remember, the complement of a 0 is 1, and the complement of 1 is 0. Now let's look at the truth tables for these two types of gates. So as we recall, the only way to get a 1 with an AND gate is if both inputs A and B have a 1. Besides that, it will be a 0. In the case of a NAND gate, when both inputs A and B are on, the output will be off. So as you can see, this column rather, is the complement of this column. Now, we could use an AND gate and a NOT gate to construct a NAND gate. So here is the AND gate, and let's put a NOT gate next to it. So let's say this is input A, input B. The output of an AND gate is AB. B, and once you use a NOT gate, it basically takes the input and gives you the complement of that. So the complement of AB is just AB prime. And so the combination of these two logic gates will produce, or is equivalent to, a NAND gate. Now here's a question for you. Let's say if we have a NAND gate, and let's say if we take the two inputs of a NAND gate and connect them together. What type of logic gate do we now have? What would you say? So it's of a NAND gate and connect them together. What type of logic gate do we now have? What would you say? So let's compare it to the original NAND gate. So this would be A and B, and we would get A times B, but the complement of that result. Well, now we only have one input, because both of these will be A. And so if we multiply these two, it would be A times A, and then we'll get the complement of that. What is A times A? Now you need to be familiar with some rules of Boolean algebra, and we're going to go over those rules soon. But A times A is basically A. One way to help you see this is if you multiply 0 and 0, you get 0. If you multiply 1 and 1, you get 1. Now keep in mind, we're dealing with binary numbers. And so in a binary system, this is it works out to be true. A times A is A. So this is the same as the complement of A. So notice that we went from A to A prime. This is the equivalent of a NOT gate. So that's how you could use a NAND gate to make a NOT gate. So these two are functionally equivalent. Now, let's understand how this works using a truth table. So let's write the truth table of a NAND gate. So about the